So let's start with question 5 here. So we have this random variable x, and we're working off practice exam B. This random variable x denotes the amount of rent the average student in Indiana colleges spends on rent. I repeated rent twice there. So it follows a normal distribution with a mean of 460 and a variance of 10,000, right? So we have this normally distributed variable, and we want to know what's the probability that the student's rent is greater than 600. Right? So we're starting out, all we have is this random variable x, right? We know the mean, and we want to know what's the probability it's greater than 600. So what we're thinking about there is we have this random variable x. It's a normally distributed, and it was normally distributed around, I already forgot. Was it 460? Okay. And we want to know what's the probability it's greater than 600. I believe was what the question asked. So what we need to do, right, is turn this normally distributed variable into a standard normal distribution. Once we have that z value for 600, we then want to find the area to the right of it. So, first of all, right away, I know this probability has to be less than what value? The area to the right of the mean, 50%. Yeah, has to be less than 0.5, because the area to the right of the mean is 0.5. Also, probably would help if I had this plugged in. Okay. So the area to the right of the mean is 0.5, so we know that this area has to be something less than that. Right? So we go to our formula sheet, and just kind of as a reminder, so here is our uniform distribution equations. If we just have a normally distributed variable, this is how we're going to find the z-score. We just subtract the mean, divide by the standard deviation, right? So just to kind of remember, our mean was 460. Our standard deviation we don't have. We have our variance. We can find the standard deviation by simply taking the square root of that, right? So, what was this? It was 100,000? 10,000, okay. So our standard deviation, I don't know why these things die so quickly. Our standard deviation will just be the square root of the variance, which was 10,000 or 100. Right? We then plug in the cutoff value that we're interested in, which was 600, minus that mean of 460, and then we divide by that standard deviation of 100. Right? So if we do that, I think we should get 1.4. Right? So here we've got a z value. Let me see if I can get this to work. Down here, can't get this over. Of 1.4. So I'll look that up on my standard normal distribution table. Standard normal z tables. Scroll down here. 1.40. The area to the left of it is 0.9192, right? So that's my answer, right?
No, that's subtracted from 1.
Yeah, right. So if I remember what I initially said, I said this has to be less than 0.5. So I automatically even knew that I was either going to be A or B here. And what I found was, when I looked it up in the table, that was the 0.9192, I believe it was. Yeah. That was the area to the left. I wanted the area to the right. So 0.0808. Yeah. So 0.0808. So we knew it had to be one of these two because we said it had to be less than 0.5. From there, we kind of calculated it's going to end up being D. Do you have a question there? You're about to. Okay, I thought you said something. So that's 5. What if we want the probability that rent is less than 500 or greater than 520? Okay. So less than 500 or greater than 520?
You mean less than 400?
Less than 400 or greater than?
Yeah.
Okay.
It's less than 400. Less than or equal to 400.
Okay. less than or equal to 400, greater than or equal to 520. So let me get my eraser here. I'll work from this side. So we've got the same kind of setup. $400, so we wanted less than 400, greater than 520. Okay. So what we're going to do, turn these values into z-scores. I can find the area to the left here and the area to the right here. So I'll do this one first. So 400 minus 460, and I think we had that standard deviation of 100. So a z-score of -0.6. So I'm going to look that up in the standard normal table. Go here. So -0.6, 0.2743. 0.2743. Now I can go through the whole process again, turn this into a z value, but what should that z value be? Notice 400 is 60 away from the mean. 520.
So it's going to be the same area, so that way.
Yep.
You just multiply that value by 2. Right?
Exactly. It's going to be if it's the exact same distance. Remember, the z values are the number of standard deviations away from the mean. So it's the same number of standard deviations away. It's just above, right? So here, you know, I've got the same area to the right as I had the area to the left of the negative value. So I can add them up, multiply 0.2743 by 2, which should give me what? 0.5486.
Yep.
Right? So that is how we would do that one. So 0.5486. So the exam is going to be set up kind of like this as well, where I give you this information, I say use it for the next 4 questions, right? So we've used it for 2. We're now going to use it for these as well. So let's assume we took a sample from that normally distributed variable, and let's assume that we took a sample of size 25. What would the mean and variance of that sample means distribution be? So one thing that we had said was if we sample from a normally distributed variable, or we take a sample size over 30 from any variable, we know that the sample means will be normally distributed, and then will be normally distributed, and the mean of those sample means will be whatever the original population mean was. Okay? So for us, that was 460. The variance of our sample means is just the original variance divided by our sample size, which means if we wanted the standard deviation, it would just be the square root of that, right? That was kind of the denominator in a lot of our hypothesis testing problems. So the mean of our sample means is that population mean of 460, and I can't remember if we were asked for the variance or the standard.
Well, it's the, I think it's the variance.
Yep, the variance. Yeah, we're asked for the variance here. So we should just take, we're plugging things in here. And what? 10,000 divided by 25. Right? So, what is that? Do that. So 4 times 10, so 40. 400? Yeah, 400. Double checking my math here. So if we do that, we'll get a variance of 400, and then we had that mean of 460. The only other thing I could do differently here is maybe take the standard, or ask you for the standard deviation, in which case you would have done this the exact same way. Just when you got to this point, you would have then also taken the square root. Okay? So not too bad. The next question says, what's the probability that rent is greater than 475 but less than 500? Right? So now we're looking at the sample means, and we're wanting to find what's the probability that it's between, essentially, 475 and 500. Right? So I'll kind of get rid of this for right now. we can remember that the mean is 460. So once again, right away, I know this probability has to be less than what value?
0.5.
0.5, right? The area to the right of the mean is 0.5. We want something less than that. So we can rule out C and D. It's going to be A or B here. Okay. What we then want to do is turn these values we're interested into z-scores. And we want to find the area in between. So how do I find a z-score when I'm dealing with sample means? We go to our equation sheet or formula sheet, and kind of where I was using, how I knew what the equation for the variance of my sample means was, that would be right here on my formula sheet. If I want to calculate the z-score for a sample mean, I subtract the population mean and then divide by, remember this denominator is the standard deviation of my sample means. Or I can just plug everything in here. Right? I've got all these pieces of information. So for that first value of 475, I'll subtract the mean. I'm just plugging those values into that equation. Now, I could plug everything in the denominator here, or I had already calculated this ahead of time, which I knew the variance is 400, so whatever the square root of 400 was, and I could plug that in. Right? So I could break this down into steps if I wanted. If I do that, what do I get here? So 20, so 15, so 0.75, is that right? Hold on, 47. Yeah, 15 divided by the square root of 10. Yeah, 0.75. So here, we get a z-value of 0.75, right? We can do the exact same thing for 500. It's the same equation, we just plug 500 in here. Okay. So I think that will be a z-score of 2. So we're going to go to the standard normal table. We're going to first look up 0.75, find the area to the left of it. We're then going to look up that z-score of 2, find the area to the left of it. We'll subtract the smaller one from the larger one, so that all we'll be left with is what's in between. Right? So we go to that standard normal table. No, sorry. We look up 0.75, so 0.7743. Write that number down. We then go down to 2, 0.00, 0.9772. Subtract 0.7743 from 0.9772. And we should get, so 0.9772 minus what did I say? 77, oh, it's 34. 0.2038. Right? So that'd be A. Right? That's the general process. Okay. Any questions on any of those problems? Just kind of a reminder. So we found the area to the left here was like 0.77 something. Area to the left here was 0.99 something. We subtracted the smaller from the larger, and that's how we got our answer. Okay. All right. So let's work through. We'll do a confidence interval and then some hypothesis testing stuff here. So let the random variable P represent the population proportion of U.S. household owners households who are dog owners. And a sample of 100 homes, you find that the sample proportion of people who own a dog is 0.4. Right? So let's say we want to build a confidence interval for this sample proportion. Okay? Now, first thing we could check, although I don't think we can rule anything out here, is this sample proportion should be in all these confidence intervals for them to even be possible answers. Sure enough, it looks like it's within all of them. So can't rule anything out here. So what we're going to do is go to our formula sheet. We've got our 3 different types of examples that we could create confidence intervals for. One, we have a sample mean, and we know the population variance, in which case we use that standard normal, that z-table. And the equation kind of reminds us of that. We then have a sample mean and a sample variance, in which case we would have to use the student t-table. Well, the example that we're dealing with is a sample proportion, so this will be our confidence interval equation that we want to use. And it reminds us that for proportions, you use that standard norm or that z-table. So one thing going into the exam, I would maybe write down and kind of have, I don't know, next to you, or just kind of helps you navigate the confidence interval, but also the test statistic formulas. Anytime you see the word proportion or the notation for a sample proportion, you should automatically be thinking about, I need to be using the z-tables or the standard normal distribution for these problems. If you're dealing with a sample mean, that's the only time where you have to kind of differentiate between, am I using the student t or the standard normal? So if you're dealing with a sample mean problem, if you see the word sample mean and you also see sample variance or sample standard deviation, right away you know you need to use a student t. So if you see that word in the problem, sample variance, sample standard deviation, you know for those problems you'll be using that student t. But we have a proportion example, so this guy right here, we found a sample proportion of 0.4, so we plug that in here. We had a sample size of 100, so we plug that in. The only thing left we have to do is find the z-score that gives us alpha over 2 in each tail. Right? So what confidence level did we want? 95. So the 95% confidence level, our alpha is 0.05. So essentially what we're trying to do here is we've got this sample proportion. We want to build a lower and upper bound. And the way we do that is we go a certain number of standard deviations to the left and the right. So we want to kind of find this number of standard deviations. We go to the left and the right of kind of what we found. Kind of think about that as like our z-score we're looking for. That gives us alpha over 2 on either side of our interval, which if our alpha was 0.05, would give us kind of 0.02 on either side of our confidence interval. You can almost think about this. It's like if we were basing the normal distribution around the sample, it's kind of like a two-tailed test. So we know the area we want in the tail is 0.025. So we go to that standard normal table. Where's 0.025? Looks like it's right here. That's the area that we want in the tail. So that's, we look, these values in the middle represent the areas in the lower left tail. So negative 1.96, right? That was the last thing that we needed. We plug that in. Now it's negative 1.96, but remember, I mean, that's already kind of built into our confidence interval equation. So we would subtract this margin of error here to get the lower bound. We would add the margin of error to get the upper bound. So I'll do that right now. So 1.96 times the square root. Oh, I made a mistake. Hold on. Oh, there we go. So 0.304 is approximately that lower bound. So 0.304. Now notice I can calculate both the lower and upper bound here, but once I have one of them, once I have that lower bound of 0.304, I can identify what the correct answer is. Okay. And that might be a way to kind of save some time. If you got additional time at the end, you can go back, double check, calculate the upper bound as well. But once you have one of them, you can identify the correct answer here. So we're supposed to use this information for the next 5 questions, right? So we're using that sample proportion and sample size that we found. And now we're saying that there's some media source reports 36% of families own a dog. You want to test the hypothesis that the proportion of families who actually own a dog is greater than 36%. So in any of these times where you have to identify the null and alternative hypothesis, I'm not trying to trick you. Like whatever you're trying to find or whatever you're testing for, that is your alternative hypothesis. You then assume the exact opposite is true or that the complement is true, and that becomes your null, right? So if I want to test for whether or not the proportion is greater than 36%, that is the true population proportion greater than 0.36. Right? I assume the opposite is true, which is that it's less than or equal to 0.36. So if this is my null and alternative hypothesis, what type of tailed test do I have?
Right tail.
Yeah, greater than sign in my alternative hypothesis, so a right-tailed test. So when we get to problem 11, thinking about critical values, right, for these 3 different significance levels, right away, one thing, and this kind of applies to just more problems than just this one, this is kind of a general discussion I want to have. Excuse me. So if I'm thinking about my critical values are coming from this standard normal Z table. And it could come from a student t-distribution, and these same principles would apply. We know that the mean of my standard normal distribution or my student t-distribution is 0. So if I have a right-tailed test, I'm looking at the right side of this distribution, my critical values, right, that give me alpha in the tail are going to be positive, right? They're to the right of 0. So for a right-tailed test, my critical values that give me alpha in the tail are greater than 0. For a left-tailed test, the critical values that give me alpha in the lower left tail, those critical values would have to be negative. And remember when we had a two-tailed test, we said that we had critical values that give us we have pairs of critical values. It's just that now alpha is kind of split up into both tails. So for a two-tailed test, our critical values are actually going to be what gives us alpha over 2 in each tail. So it's kind of like with confidence intervals, because we have alpha over 2, right? And we have 2 tails. And then it's going to be a pair of critical values here for the two-tailed test. So this might be something to have kind of written down going into the exam as well to kind of help you remember, yeah, right-tailed test, I'm finding the area in the right tail, so it's positive critical values. Left-tailed, negative. Two-tailed, I have a pair. Okay? So right away when we look at these answers, which ones can we rule out? Well, we had a right-tailed test, so A and D can't be it. Right? From there, we just have to kind of decide between B and C. Once again, I can look up one of these alphas. I can look up like the 10% significance level, and then I can, that'll help me identify which of these is correct. So alpha is 0.1. So we did only have a right-tailed test here. So what value would give me 0.1 in that upper right tail? Well, if I try to look this up in the table, remember the table always looks at the area to the left. So I would actually want to look up 0.9. Or I could look up just alpha and remember that it's a right-tailed test. So I'll kind of show you both ways. So if I looked up that area to the left of 0.9, go here, scroll down. So it looks like we're right here. So 1.28 and 1.29, so 1.29. Or I could have looked up the alpha value of 0.1 and said negative 1.28, negative 1.29. Okay, I know it's 1.29, but it's a right-tailed test, so it's positive, right? So either way, I could have come up with that. Once I have that, I can kind of identify, well, it was in between 1.28 and 1.29, so this is going to be the correct answer. Right? Now, I could actually do this another way as well, right? Which is, I guess, I won't say it's cheating, but it makes it a little bit easier. If I go to my student T table and I remember this very last row, if I had a student T distribution that had an infinite degrees of freedom, it would be a standard normal distribution. So this last row tells me the values for the standard normal distribution that give me these different areas kind of in the tail, right? So I can look them up all three pretty quick. 0.1, 0.05, and 0.01 for a standard normal distribution would be 1.282, 1.645, 2.326, okay? Which is exactly the values that we see right here, okay? So once we have those critical values, kind of usually the next step is what's the value of our test statistic? Well, we have a proportion. This is kind of a question I've seen pop up. How do I identify which test statistic equation I use? Well, if I'm looking at my formula sheet, this is a sample proportion, right? If I'm dealing with a problem where I'm given a sample proportion, I should be choosing the test statistic, which here are your test statistics. Once again, I'd print this out, write it next to here, get a Word document, insert a little text box here that these are your test statistics. Here is the one for our sample proportions. So I plug in that 0.4, which is my sample proportion. P0, remember, is the assumed true proportion, which is going to be coming from your null alternative hypothesis. So that was 0.36, right? And then 0.36, sample size of 100. At that point, it's just a matter of getting this entered into our calculator correctly, right? So what is it? I said it was 0.4 and 0.36, so divided by the square root of point. Come on. So 0.833 repeated. 0.833 repeated. Now, one thing to kind of prevent us from making an easy mistake here that we could have thought about was what we're doing is we've assumed that the true population proportion was less than or equal to 0.36. So we can use that as kind of our assumed true value, that 0.36. We found a sample proportion of 0.4. So if I think about, if I'm turning this into a test statistic, what I'm really doing is turning it into a z-value, is a z-statistic. Excuse me. So if I see something above the mean, well, this assumed true mean would just have would be a z-statistic of 0. So same kind of idea we talked about before. If I see something above this assumed true value, positive test statistic. If I see something below it, negative. So right away, I know I have a positive test statistic, which means I could just cross off C, right? And if I, for some reason, had flip-flopped like the proportion and sample proportion in my numerator, I would have gotten negative 0.83. And so by kind of remembering like, oh, I found something to the right of the assumed true value, it has to be a positive test statistic, it would prevent me from ever accidentally kind of making that mistake and answering C, okay? So once I have that test statistic, the next question is generally what's the p-value. Now, on the multiple choice problems on the exam, to prevent you from making like cascading errors, if you didn't get the null alternative hypothesis right, you're definitely not going to get the critical values right, probably, right? So a lot of times if it's a question that asks you to identify the null alternative hypothesis, on the very next question I will say, assume that instead this was the null alternative. So I know that you're kind of working right from the correct place. I also might ask you for a test statistic, and usually I would give you then here, assume the test statistic you found was this, what's the p-value, right? So here, because we're working through it together, I don't have to give you a new assumed true test statistic. We can use that 0.833, right? So what is the p-value? The p-value is the probability that we saw this test statistic of 0.83 or anything further from that assumed true value, right? So here was kind of our p-value. Right? So for this right-tailed test, right, I can look up 0.83. The table will tell me the area to the right. I then need to subtract it from 1. Okay. So I go to my table, standard normal table. I look up 0.83. So 0.83, the area to the left is 0.7967. Right? So 0.7967. I wanted the area to the right. Right? So my p-value is going to be what, 0.2033. Okay. So my p-value is 0.2033 there. Right? Now, if I had also asked to make a rejection decision based off of this, what levels can we reject at? Well, remember, this is another thing. I would write this down like on if you're doing a cheat sheet or something. We only reject if the p-value is less than alpha. So my p-value, is that going to be less than 0.1? No, so I failed to reject. Well, if it's not less than 0.1, is it going to be less than?
Yeah, it's going to fail.
Right? Yeah. As soon as you know it fails at the 10% significance level, you know it fails at every level, higher than that.
But
So
if you wanted to do like what would be the 19th? No, the 21st level.
Yeah. The first level, the p-value is essentially telling us what's the first level that you could reject the null hypothesis at, right? So the first level that we could reject would be an alpha of 0.2034, right? So the, I guess 20.34 significance level or just under 80% confidence. Yep. Okay.